We have Dr. Hengshuai today. He's a senior staff scientist at Huawei and an adjunct professor in the computing science department at U of Alberta. He will present today his talk on learning to accelerate by methods of step size planning. So over to you, Hengshuai.
Thank you for the introduction, Yinji. So welcome to the talk.
Hi, everybody. Welcome to my talk. Today, we're going to discuss an interesting topic in gradient descent, which is the step size. So gradient descent has a long history. So throughout the talk, we're going to use this figure. We don't need to understand it now. So this figure will be used to explain the 4 ideas in the paper that I wrote recently. This talk is based on this paper. Here are some, the lost contour just reminded me of the universe, the galaxy, the shape, which is quite interesting. So gradient descent has a long history. Its problem also has a long history. We know it well that gradient descent is slow, suffers from ill conditioning. Step size requires lots of tuning, and there has been numerous efforts in adapting step size. To name a few: Polyak step size, DBD, IDBD, auto step, Adam, MetaTrace, TDBD, geometry-aware gradient descent. I highlight those with yellow color, the bright ones. Those are the efforts by our departments. So the paper I talked is called Learning to Accelerate by the Methods of Step Size Planning. It's quite a fancy title, but interesting topic. So here, first thing you notice, learning, step size learning. Since we talk about learning, what data are you going to use? How is this possible? So if the data you use is so special, why the other people, why prior methods, they don't do it this way? I'm going to discuss diagonal step size, which is a diagonal matrix form of step size that's going to be applied to the gradient gradient vector. So second order people may think or say, don't we need full size of the matrix? You know, matrix inversion of a Hessian. Don't we need that? We're going to discuss this in great detail. So step size planning. So we talked about step size learning. Seems already crazy. Step size planning. Everybody knows planning here. It's a reserved word in reinforced learning as a process of solving a model. It's a model-based reinforced learning. So your algorithm is applied to gradient descent. How come it's planning? So, and crazy enough, the planning algorithm, the step size planning algorithm in this paper come up with a negative step size sometimes. It's quite weird given the vast literature of gradient descent. Many forms of step size have been used, but all of them are positive or can approach 0 when you take the time to limit. So this is, for some of you, this is going to be a very crazy talk. It's easy to me, you know. Even, you know, I'm so influenced by second order methods, by Newton methods, by preconditioning methods. So this has lots of things that's very crazy. But let's take a very light title for the talk. A roller coaster view of gradient descent. So why roller coaster? Why roller coaster are real life examples of smooth functions. And taking a roller coaster is very similar to performing gradient descent along a convex function. So I'm going to make it more concrete. So roller coaster, everybody loves that, except me. So how do you know where you are when roller coasting? Suppose you are not allowed to look. Are you at the bottom or are you at the top? Suppose you need to measure it yourself. Nobody tells you, and you are not allowed to look. You sit tight and hold tight. Of course, you're going to take a few measurements. Hair movements, body pressure on the chair, things like this. It appears that measuring where you are is also important for our life. For the life of gradient descent, it's also super important to measure where you are. So it appears that for gradient descent, measuring where you are is the ultimate question for step size adaptation. So I summarized, no one says this, but they somehow implying this in prior methods and discussions. I summarized this from lots of papers. So measuring where you are by gradient descent itself, no help from external. That basically means gradient descent updated data has to be used in order to measure well. We talk about data. So data has been heavily used in our various AI applications. For example, autonomous driving, computer games, Atari, Go, simulators. So all of them are real data, the data we are familiar with. But here we talk about gradient descent, update data. Well, this is kind of not make a direct connection to you. So, and does it tell you where you are? Does the update data tell you where you are? So we're going to answer this question, discuss it throughout the talk. So we need to measure where we are in gradient descent update. This is, I say it this way, I summarize this way, but there are really early algorithm examples. They're already doing this. For example, the first algorithm, hypergradient descent, which is a deep learning algorithm, can be summarized in two lines. One is a gradient descent on W, the other is a gradient descent on alpha. So this is the meta gradient methods. Eta is a meta step size. So to make some sense of this step size, imagine the loss function f is convex, and we start from the green dot, which is W0. We also have alpha 0. So here we take a gradient direction. We take the gradient at the green dot, W0. We have the gradient. We do the update using alpha 0. So we are there. We take gradient again. Now notice the two gradients are in the same direction. I mean, acute angle, roughly in the same direction. So it's a positive correlation, step size increase. So we're going to do this a few times, until we shoot the other side. We shoot the other side, we shoot there, we go there, we take the gradient. Right now, gradient direction is in an obtuse angle to the last gradient. So step size decrease, arrow becomes shorter, we are there. Take gradient again. This is the same, this is a positive correlation. So step size increase, we go to the other side. So this is the dynamics of hypergradient descent. There's another algorithm, IDBD, which is very well known to some of you, and have 4 lines, virtually 3 lines. But if you ignore the exponential form of step size, so basically on beta alpha, you can just reduce to alpha. And here I have observation that IDBD and hyperdescent are related. That's quite interesting. To make the connection, here I introduce an algorithm called IDBD1. So this is just like this, 3 lines. So this has only one single scalar step size alpha, shared by all components of W. So to make the connection, notice the correlation term. The first term in the correlation gradient doesn't change, but the second gradient is replaced by a trace term, H. So basically, H is a historical average of the gradients. So here, by setting lambda to 0, we recover hypergradient descent from IDBD1. Now, how do we recover IDBD? We recover IDBD by taking the measure of correlation for individual components. So here, F, suppose is linear, then it's third, it's like this, and then it's like this. So this is very simple. So basically, another interesting side observation for IDBD is that there's the Lu operation, which is quite interesting. Don't we know the Lu was invented way later, like 20 years later, 2010? It appears this is exactly the Lu if you check the IDBD paper, which is quite interesting because this ensures lambda is positive or non-negative. So measuring where we are is done by hypergradient descent and IDBD. So IDBD seems a more general form of the idea. Hypergradient descent is a refined version of IDBD in 2 ways. First, the history of gradient is removed. Instead, only the latest gradient is used. Second, component step size is reduced to 1 scalar step size. This is quite interesting, right? But it appears that both refinement are bad. Both are bad. Why? First, without history, mirroring according to the latest gradient is noisy. It's not reliable. If it's not reliable, then that means step size adaptation is all wrong. That could easily lead to slowness or divergence. So only using the latest gradient cannot measure reliably where we are. In the paper, I have proof that using a single scalar step size to adapt by meta-gradient is slow. It cannot be faster than a linear rate for L-smooth and strongly convex functions. This is quite interesting because this rate appears to be faster than the best rate for gradient descent using the optimal scalar step size. It's faster, but just a constant faster. So in practice, actually, this linear rate is not achievable by meta-gradient. You can check the proof in the paper to see why. So instead, if we assuming component individual step sizes are used and they are adapted according to meta-gradient, then they can solve convex quadratic optimization in how many iterations? 1 iteration. This is quite whoa, whoa, really? Okay, check the paper. Okay. So for the purpose of the talk, I think we focus on high-level discussions without going into detail. So we're going to introduce a generic form of gradient descent update, which is basically the DK here is a diagonal matrix. Generic form. So DBD and EDBD use the step size for each parameter, and later research called this vector or vectorized step size. For example, see these 3 papers that extends EDBD to reinforcement learning. So I call it the diagonal step size because first, it's mathematically equivalent, but it has a better understanding of the rows of the step sizes. So this is a very general form of gradient descent. And this includes EDBD and the new algorithm we propose later. So the diagonal step size is quite generic because it can also recover the normal gradient descent update by setting all the components to the same number. So this is interesting. So before we discuss furthermore on the diagonal step size, we're going to discuss second order methods. Second order methods are quite interesting, especially given recent deep learning. And there has been many efforts towards this goal to make second order methods efficient enough for backup propagation. We saw a number of familiar names, as well as some keywords that capture the commonality between the methods. So Hessian, full matrix, Krylov, natural gradient. These are quite interesting because it shows the commonality between these methods is Hessian matrix. But we know Hessian is dense, and involving Hessian in computing, whether by inverting it or computing the Hessian vector product, it's going to be complex, order n squares. So most deep learning methods use an approximation of Hessian by referring to sparse or diagonal matrices for this purpose. So approximating Hessian is a key idea of the above methods. But the question here for you is, do we need full size matrix at all? And approximation is good if we have good purpose. For example, function approximation, especially value function approximation, we approximate the value of a state, and this also provides generalization. But it appears that for this second order methods, to make it applicable, here is just for computational efficiency. And this kind of bothers a little bit, right? As diagonal matrix is widely used in this coming up with an approximation of a Hessian, but the simple diagonal matrix can do more than approximating Hessian. So this is a key idea that we're going to explain. So approximating Hessian limits the power of diagonal matrix. It can do more beyond approximation Hessian. Okay, now we are ready to discuss the projection power of diagonal matrix or diagonal step size. So suppose we have gradient vector G, and we want to move G to a target vector denoted by Y. So we want to go there. You may wonder, why do we want to go there? Because remember, we need a projection for our generic gradient descent update. So some sort of Hessian inversion going to be computed. Or like we introduced the generic gradient update in one diagonal matrix, right? So we need to project the gradient in both methods. So we want to go from G to Y. How do we go there? It appears that we need to rotate by angle theta and scale, then we arrive at Y. So in this process, we compute a matrix A. So this is matrix A, and by projecting A on G, we achieve Y. So this is the standard linear transformation theory. But hold on, so take a look at this diagonal matrix. So diagonal matrix, this alpha, so calculate this a little bit in your mind. Alpha times G, yeah, that's equal to Y. So that equal to Y, that basically means it achieves the same function as a dense matrix A. So why is this important? The difference is order n squared or order n. The difference is whether order n squared is exact and order n is approximation, right? So because all second order methods, they use diagonal matrix to approximate hashing in some way, but this shows diagonal matrix can also be exact in projection. So were we wrong? I found this quite interesting. When I found this, I found, whoa, my education tower collapsed. Yeah, this is some moment I rarely had it before. Yeah, the education tower collapsed. So diagonal matrix, the projection power means we can accelerate beyond the Newton methods. So because diagonal matrix is expressive in projecting the gradient, and we don't need hashing or any dense matrix anymore. We are free from hashing. We are free from Newton methods in accelerating gradient descent. This appears to be a big deal. The diagonal matrix step size can transform a non-degenerate gradient to anywhere. Non-degenerate just means the component of the gradient vector is not zero. So diagonal matrix seems very expressive and very light in projection. Diagonal matrix can take us anywhere in the ND space. So remember that at the iteration k, we have our current parameter vector wk. From wk, we calculate the gradient, negative gradient direction here, but we don't want to follow here. We don't want to follow the black arrow. Instead, we want to follow the red arrow. The red arrow is a projection made by the diagonal matrix, pointing to a neighborhood of W star. So basically, the diagonal matrix can lead us there, theoretically possible. So that red arrow is possible, right? But in the paper, it's derived using the knowledge of W star. So that sounds crazy because this is a step size rule that assumes the knowledge of W star. If we already know W star, why do we need learning? Why do we need a step size at all? So to solve the chicken egg problem, the key idea is to predict WK into the future using the diagonal step size. So that basically being said, if jumping into k iterations into the future is possible, we can accelerate gradient descent in a number of steps faster. So that red arrow is possible, but how? So this is a moment where the roller coaster view can be helpful. Recall that the roller coaster view is a data view, which treats the gradient descent update as data. The question is, does the update data contain useful information at all? Useful information that allows us to learn such a diagonal step size, pointing us to the future? This is a very good research question, but no one has explored before. So likely the answer is yes. Yes. So some reflection here. Previously, we reviewed hypergradient descent and IDBD. We also draw a connection between the two algorithms using IDBD1, a new algorithm. So it appears that all the three algorithms measures where we are by some sort of correlation between historical information and the current gradient. Historical can also means the latest. So basically, the historical gradient is used in some way, but this appears not enough. This appears not enough. Just using the historical gradient is not enough. It will only be enough if we treat the gradient descent as a process of generating data. Why? Why? Because if we treat the updated data, then we can do step-size learning. We can do step-size planning as well. So this is the data view or the roller coaster view for gradient descent that makes the learning of the diagonal step size possible. So this planning algorithm is called chug. First, I'll look at the outcome of the algorithm first. So here, basically, you can see the red dot here. This is the loss contour of the Rosenbrock function. The local minimum is located at 1, 1 near here. And the red dots is overlaying dots, very close to each other because gradient descent is slow. So these are the data we collect. And these solid red lines are produced by the planning step. So basically it's collecting the data from zigzag, learning us diagonal step size from the data, and project the current gradient to the future from WK. So I promise you, you're going to understand this in a better way. So chug is algorithm. How does it achieve this behavior? So this shows us the algorithm. So it doesn't make so much easy sense, but let me explain to you the details. First, you notice I call this step size planning. This is the step size planning algorithm. Question here is this planning at all? Everybody here knows planning has a well-defined meaning. It refers to solving a model in reinforcement learning. So linear dyna is planning because it's policy evaluation and it's solving a model that is estimated from data. But here, linear dyna is for policy evaluation and chug is for gradient descent. How come they are related? How come in gradient descent you have a new word, planning? No one has used planning, this word, or techniques in gradient descent. So what exactly the meaning of planning here? So first, let's take a look at the linear dyna. Linear dyna assumes a linear function approximation of the value function. So basically, there's a feature mapping phi that map the current state to a feature vector. So at each time step, we observe the current feature vector phi, and we take action A according to the policy, from which we receive reward and the next feature vector phi prime. So based on this transition experience, we can define TD error and TD update and perform TD learning. In this case, it's TD0. It appears that in Chag, at every time step, we also have an online update procedure, which is GD or SGD. So this is one-to-one correspondence, the learning part. So linear Dyna also has another part of F. F is basically a transition matrix or transition model. So what it does is predicting the current feature, predicting the next feature vector using the current observation, using the current feature vector by projecting on it. So this is minimize the prediction error of predicting the expected next feature vector. So here B predicting the reward, but reward is just a special feature. You can basically view B lowercase b, the reward model, as an extended row from the transition matrix F. So we can ignore B. So in planning, it's just a matter of using the model. In each planning step, we sample a feature vector phi, and then we project it using matrix F to produce the expected next feature vector phi prime, from which we have TD error, TD update, all well defined, and for which we can perform TD learning. So this is basically linear Dyna. So it appears that the matrix F update also have a one-to-one correspondence in Chag. So the alpha there serve as a transition model. But the difference is, so both are modeling. The difference is in linear Dyna is a single step model. In Chag it's a multi-step model. It's quite interesting. So in planning, we do projection, we do TD updates. And here we also have projection applied, projecting the gradient. And this projection predict the future updates. So this is planning. So architecture-wise, you can see the two algorithms are strikingly similar. Everything you said about linear Dyna in architecture can be said about Chag. To make a try, Chag is an integrated architecture for learning, modeling, and planning. So this sounds really familiar. So here, the green box here we didn't explain. It's just the data collection and data processing part. For data collection, this is just putting the update into key steps away from each other to form multi-step transition. So alpha can be learned. You can look at the detail how alpha is learned in this way. So as promised, alpha projecting the gradient produce what is promised, the red arrow. The red arrow is projecting the gradient and targeting at future iteration. Review the previous 3 slides. Let's review a little bit to make sure it's understandable. So we present Chag, we discuss how Chag perform in action. So data collection, data collection, I'm using green dots to circle the area where we do the data collection from gradient descent. So gradient descent being slow, a single red dot appears a single dot, but actually it's many overlaying dots together because gradient descent is slow. So this part, the gradient descent update on the loss contour appear to be zigzag. This is also the data. So we arrange the data in multi-step away from each other. And this is exactly the data. And the red solid line is correspond to the planning procedure. So projecting the gradient with the diagonal matrix. This appears to be everywhere where the red solid line. And this is exactly the red arrow as we explained in this figure. So you can see, so take a few moments for this algorithm and how it works in practice to get some understanding why it's fast. So, okay. Now I think it's time for some performance measures. So here we use Rosenbrock function, which is a famous and challenging function for optimization, especially gradient descent. So gradient descent takes about 10,000 iterations for 10 to minus 3 accuracy. You may see 10 to minus 3 is already good, very good. Why do we need more accurate? Well, this is not deep learning. And all these accuracy numbers make sense when we compare to each other. So now the meat, which is a heuristic method, is way faster than gradient descent because it's not based on gradient descent. So it spans fewer than 200 function evaluations for a great accuracy. Adaptive coordinate descent spanned about 300 function evaluations for the same accuracy, and TRAG span below 500 gradient evaluations for 0 error. So here you see, the numbers roughly make sense and seems close, but they are actually different things, right? Different metrics because they use different information. Function evaluations and gradient evaluations are very different. In deep neural networks, gradient evaluations are way slower. So that basically means CHAG has lots of potential for deep learning. So you might have noticed there's a negative value here in alpha 2, so alpha 2. So this alpha 2 can actually be way more negative than this value showing here. Negative step sizes, negative values. Why does it make sense? Well, look at the literature. All areas of using gradient descent, including first wave of neural networks, including PDE solutions, including OLA methods, including deep learning, deep reinforcement learning, everything, everywhere where gradient descent is used, you will see different forms of non-negative step sizes being used. Here, showing an example in IDBD, showing step size should be some sort of exponential form. Well, yeah, but why do we do that, right? If negative step size makes sense, then we don't need to do that. So let me explain to you, even in the deterministic case, it makes sense to use negative step size. Why? Here, that's the x-axis being W1, the y-axis being W2. Let's update gradient descent from point A to B. So A to B, gradient descent update. So you can see from A to B, we make progress in W1 because W star is at the right-hand side of A, right? So, but from A to B, we make a downward motion. This is a backward motion that lost the progress of our gradient descent in W2. We lost progress in W2. So that basically means for fast convergence, we need a negative step size for W2 and a positive step size for W1. That explains why we need negative step size in even in deterministic gradient descent. So in the stochastic case, SGD, it also makes sense to use negative step size. Why? So first, in the stochastic case, the true gradient is never known to us. So we don't know this true gradient direction, but instead we can sample it. Since it's a sample, it can be anywhere. So the red arrow here, it appears to be beta samples. Why? Because it forms an obtuse angle with a true gradient. So performing gradient descent using positive step size appears to be go along this way, which means that that's gradient ascent, right? We made a mistake when the gradient sample are bad. Instead, we should use a negative step size when this obtuse gradient for short happens. When this forms obtuse angle with the true gradient, we should actually use negative step size, which will perform gradient descent for the true gradient. That's kind of interesting and makes sense. Of course, the averaging effect of using stochastic gradients, using many such gradients for updates, you will achieve the averaging gradient somewhere near the true gradient. So, but really bad sample can happen. That basically means certain parameters need to occasionally back off, not always go along the negative gradient direction during updates. With both positive and negative component step sizes in the prospective sampled loss, some parameters go gradient descent, but some others parameters go gradient ascent for faster learning. This sounds really weird. I take a few moments to comprehend this. Okay, so I also have an example for people who love convex. But before present the convex problem, if we have time, let's briefly summarize the presentation. So we promised we're going to use this single figure to illustrate the 4 ideas in the paper. So 4 ideas. First idea is a roller coaster view of gradient descent. It's a data view. We should treat the gradient descent update as data. Second, using the gradient descent update data to learn and plan step sizes is possible. So Chalk is the first such algorithm. It learns the diagonal matrix step size. Third, the diagonal matrix step size has the same projection power as a full-size matrix. Fourth, the step sizes can contain negative values, which enable faster convergence for ill-conditioned and non-convex problems. So this is the end of the talk. I think we better give time for questions and discussions. So if there are more time, we can discuss the convex problem. For now, let's take questions.
Thanks for the talk, Hengshuai.
Thank you.
The questions I have verge on what you may speak about when you talk about the non-convex problems, but I can ask a question that relates to two things. One is that I think what you've developed is a set of general sampling methods for gradient ascent or descent that relies on the data, that is on the attributes and the dimensionality of the data, which seeks to provide a model or identify a model in the data to be able to make choices about, for example, sample size. I think that that's good. So the two questions are, do you think that we could put this into variable rate sampling and that we can run them all in parallel on the same data and produce as output increasingly accurate, but starting with approximate shapes of the multi-dimensional domain that you first look at? And then the second one is related to this in a somewhat biological way. There are variable resolution evolved systems like the human eye has focal points in the retina that have high and low resolution that adjust according to where we're looking. And they do that because we want to be able to know in our periphery how to identify attributes of the coarse models in our visual field, and then choose whether or not to focus at the fovea to be able to get higher resolution things. Partly what you have seems to be a system that could be deployed to provide, if you like, multiple resolution. And this applies everywhere. For example, it applies in communications when you do variable aperture model building depending on the rate of communication and data capture. So two big questions is, can you develop something that would give you approximate shapes of the non-convex domain so you know what to watch out for? The second one is their relationship to this multi-resolution foveation like in human eyes.
Yeah, so the question are big. I haven't thought about that, but to clarify, the data here is, I think the data you mean, and maybe it's different. I think the data Randy means is real data. So here, the data is some sort of the update data, which means between iterations, you know, how the model changed. So this is kind of another data that has been largely ignored, which is the data view or the roller coaster view. What I mean.
Yeah.
Right?
So you're treating directly the dynamics of data that isn't unfolded, but you could, in principle, step back and say, what is the general shape of the data I've seen so far? So you could do a retrospective construction of a model, for example.
Yeah, but I appreciate your question in this way. So basically, so by allowing negative values and positive values and using diagonal matrix step size instead of a single scalar one, you actually explore the parameter space much more.
Yes,
so
I agree.
So in that way, that might be related to the second question. So the adaptive focal length on visual systems, right? It's a matter of freedom, degree of freedom. So in robotics, we have degree of freedom. So here, basically, by extending scalar step size to a diagonal matrix form, we increase a degree of freedom. We increase degree of freedom. The benefit is that you can observe the parameter space in a much better way. Right? You have better way of observing.
It's a nice metaphor because increasing the degree of freedom is kind of like taking a step back. Yes.
Right.
Okay.
So this paper, yeah, I really think, you know, I experienced lots of weirdness in developing the idea. A lot of things that I talked today didn't make sense to me at the first moment or in the first months I had the idea. It's lots of thinking and rethinking, and so very weird talk. I would say if you you know you are interested, anyone is interested, I'm very happy to discuss. Yeah.
Just a final comment is that, yeah, is that you mentioned this can apply to reinforcement learning or deep learning. In general, this applies to all learning. And as I come from a background where we wouldn't consider not building model-based, not doing model-based learning. So it's a nice, refreshing view. Thank you.
Thank you, Randy.
Any other questions? Please feel free to unmute yourselves and ask Hengshuai directly.
Maybe I missed something, but does this algorithm guarantee to converge? It seems like it's not.
I think you are the author of Hypergradient descent, right?
I gave them related work.
Yeah. Are you Mark Schmidt?
Yeah.
Yeah. So first, thank you for coming. So about the convergence, I'm not sure. I haven't developed the convergence guarantee, but in the experiments, I sort of have some sort of observation that it can have very bad behavior, can deviate from where the minimum which direction is located, but it can deviate. But then I fixed this issue by adding gradient descent update or SD updates in the planning step in the inner loop. So it fixed the off-track behavior. So that problem of off-track behavior will become more pronounced as you extend it to multiple times of planning. So there's no proof, short answer. Yes.
Yeah, I mean, I suspect that this is going to have the same trouble that all the quasi-Newton methods will have, because it's very similar to quasi-Newton methods, and they end up having big-time convergence problems, unless you add a line search or something like that.
Right. So for a person like you, you know, my experience on optimization is time is very limited, very short, just 2 years. I just started, like, you know, my previous research on model-based IO. So I learned a lot from the hypergradient descent. So I made a comment that maybe a little bit superficial. Maybe it is superficial. So I think the connection between hypergradient descent and IDBD is interesting, and it's quite interesting to see meta-gradient methods works for deep learning. So yeah.
Yeah, just to support Mark's question, I had a similar question about convergence, or at least predicting convergence at different parts of the space by having this variable rate. I think that that's important. So I don't think that this solves the whole problem, as Mark points out, but I think what it does is it may give you a tool to be able to investigate the complex manifolds in these shapes that are, you know, what combinatorial optimization people will try to slice a complex problem into only convex pieces that get stitched together. So maybe this will provide insight there too.
Yeah. So I'm still working on understanding of this algorithm, and some Mark's comments on the convergence issue. Those things are not clear yet. So that's why I focused on gradient descent only in this paper instead of way popular STD algorithms. So yeah, thank you for thank you, Mark, for the comment.
Yeah, he sent a text, gotta go to next meeting. Thanks for the presentation. And Abhishek Naik also has a message for you saying, I have to leave now. Thank you for the presentation. So
Thank you.
any other questions? If not, Hengshuai, I don't see your email ID. If someone wants to reach out to you, how should they contact you?
Just my email. I will send you later. So
Okay.
yeah.
Wonderful. So thanks for a great presentation and wonderful discussion. I think you are meeting other students as well today. Some meetings are scheduled.
Oh yeah, I can take a look at the schedule later.
Sure. Wonderful. Thank you so much for presenting today, and thank you everyone for joining in. See you next week. Stay safe, everyone.
Thank you, everyone. Thank you. Bye.